Hello everyone. Today I am going to present the XGSLab software and we'll be stepping through the GSA tutorial documentation referencing the EN 5522 standard. You can find this documentation in the start page by selecting the tutorial links and going to the XGSLab software for pulling the DXF that we'll be using for our grounding system layout. So I'll go ahead and start this project by creating a new project in my directory. Let's just call this GSA. And once we have this project open, I'll now select the project module. So we'll be using the GSA, the grounding system analysis module. Now you can see I have some tabs that have appeared. I have a project information where I can enter in some of the design considerations for the site and document some of the decisions that were made. You can also add your logo so that you, when you're exporting the report, can have that integrated into the summary report that's exportable from XGSLab. We do want to select our reference standard, and as I stated, we'll be using EN 5522. And in the next stage of this is we're going to create our soil model. So you can enter in the soil model if you knew the electrical characteristics of your site. Most of the time you're going to receive some resistivity measurements, and those can be entered into the XGSLab software. Here there's a figure indicating the purpose of each of these columns. So we have our A column, which represents the space between voltage probes, and the C column, which represents the distance between our voltage probe and current probe. If we're using some of the traditional Winner or Schlumberger methods, this allows us to enter in that data. So I'll go ahead and just take the measurements from our tutorial documentation and paste that into the soil analyzer, and you can see on the right we have a preview of the resistivity measurements. Down below there is an automatic detection checkbox. This allows XGSLab to determine automatically the number of layers that can approximate the soil resistivity measurements. Today we're going to follow the tutorial documentation and just force it to a 2-layer model, run our calculation, and we can see a relatively low RMS error indicating a good curve fit to our resistivity measurements. And we can view that in the results group box. So I'll just take a snap of this image, and that is going to be saved for our automated report. The next thing we need to do is actually create our grounding system. So we can do a hand-drawn system in XGSLab software. So I'll just set my horizontal length, if I want it preset, to 10 meters. I can do that. Of course, if I were to zero out the LH, the preset length, then I can draw a conductor of any length. And of course, there's some drawing tools to help you when you're developing your system by right-clicking on each of the conductors. But we're actually going to import a grounding system. You can find the DXF on the XGSLab website and download it from there. Here is a grounding system. Shown in red are our grounded conductor that is inside the substation that's surrounded by a non-conductive masonry fence. Outside of the substation, we have a buried tank. And what's interesting about this drawing is the tank is drawn three-dimensionally, while our substation grounding layout is drawn in a more two-dimensional common CAD approach when doing a grounding system layout. So we're going to go and import this into XGSLab. So I'll go to the import export, navigate to my DXF file, then set my scale. And the next thing I want to note is this Electro data settings group box. So the way you can look at this is more of a template for the drawing that you're going to create or what layer you're going to import. So here we have a horizontal conductor with a diameter of 10 millimeters. And this works like a calculator. So if I change the cross-sectional area, you'll see the thickness change to correspond with my diameter and my cross-sectional area. We can also go this way. There's a horizontal and a vertical configuration, and as I import my first layer, you can see how this will affect your importation. So if I select the E-grid layer that corresponds to the red conductor that we had seen earlier, I'll set this to electrode 1, meaning any current that I set in electrode 1 is going to energize conductors that are in this category. And this is how GSA works. If you're using the other modules, you'll want to check out those tutorial videos because it works a little bit differently from GSA to GSA FD. Now, by selecting my tilt, I'm importing my Electro data settings templates. And I need to adjust the depth of my grounding system because that drawing you saw was two-dimensional and we need to actually shift our grounding system into the soil 0.7 meters. Now I'll apply this. And let's also import that buried tank adjacent to our substation. So I'm going to navigate to the tank layer, and I don't want that tank to be energized by the same fault current that I'll insert to electrode 1 or my grounding system for my substation. What I do is set that to electrode 2, and this allows me to either energize that with a separate current or leave it as a passive system so that you could evaluate voltages transferred to it. Now I can set my horizontal tilt. I don't need to adjust my shift. I will change the electrical characteristics from copper to steel. Let's apply that. Finally, there are a lot of components here that really don't play into our grounding system analysis, but are kind of important to know their location. So we'll call those the background components. So we can import that information just as a reference using our background checkbox. And I'll apply this as well. So I'm just going to set my fragmentation for the import to low. This is splitting the conductors into smaller segments, and I'll go to the import and export group box and select the import button. Okay, our importation is completed, and we have a long list of conductors that we've imported. This is a filterable list, kind of like what you would expect from Excel. You can check the length of conductors, their depth. This is a nice handy way to quickly verify that there wasn't anything misdrawn in your DXF, and just makes it easier for checking. But to actually visualize the system, you can click on the draw, and this will take us to our view of the substation. And here we can see we have the substation grounding system has imported. We have our tank that is buried adjacent to our substation grounding system. And you have a YZ and an XZ plane. You can see in this substation that we have not incorporated any ground rods. In your importation, you can account for those by referencing the block in AutoCAD or MicroStation or your other drawing tool and converting a two-dimensional drawing into a three-dimensional drawing. For this example, we're just using the horizontal conductor layout. So the next thing I want to do is actually energize my system. So I will insert 1 amp test current into my substation grounding system. And I'm doing this just so I can understand the grounding system resistance or its impedance, so I can use that in my future split factor calculation. So we'll go ahead and hit the debug button, and this is checking my grounding system layout, checking for errors on the importation, looking that I have an energization to actually analyze, and I can check my messages window at the bottom here. I see my importation was successful, so I'll go ahead and compute my analysis. Okay, my analysis is completed. I have a new tab that's appeared, and I can select this GPR and earthing impedance button. And here I have a table with electrode 1 and electrode 2, electrode 1 representing my substation. And I can see my impedance has been calculated to 0.3253 ohms. So this is the information I need in order to determine my split factor. Going back to my project tab and over to the split factor tools, I can enter in that 0.3253 ohms with my fault current of 5,000 amps. And then I'll just enter in some of the other reduction factors or split factor considerations that are provided in the GSA tutorial documentation. And I'll add this in, hit calculate, and here we can see that of the 5,000 amps, it's expected that approximately 3,000 of that will contribute to an earth potential rise or ground potential rise by going through our grounding system. The other portion is going to take alternative paths such as neutrals or shield wires to return to its source. So we'll just apply this and then check that that was applied to the correct electrode. You can see here it's imported correctly. Before I go to the next stage, I want to do a couple things. First, in my soil tab, I will incorporate a crushed rock gravel surfacing. We'll just use an assumed 3,000 ohm meter. That's approximately 100 millimeters thick or 4 inches thick. And I want to calculate my permissible touch and step voltage limits. You can type these in, or you can also use the calculation tool. So I'll type half a second clearing time. We're not going to add any shoe resistance or glove resistance, and we'll apply this to use for our touch and step voltage plots once we've reanalyzed our system. So the next thing we want to do is recompute our analysis with the actual fault current. So my analysis completed, and I'll go to the GPR and earthing impedance button again. Here you can see I have the 3,258 amps. I still have the same grid impedance, and this results in an approximately 1,000 volt ground potential rise or earth potential rise. You can have some interesting plots from this group box, such as the current leaving the conductors. But when doing a grounding analysis, we're most often looking for calculating our touch and step voltages around our substation. So you can draw a window or hand type your coordinates that you would like to evaluate your system. Just check that I got this view, and I'll hit the calculation button. So my operation has completed, and I can start plotting my ground potential rise, my touch and step voltages, and I think the first one we'll do is just a 3D plot of the earth potential rise or ground potential rise. So I'll save this as an image for my report that I can export from the XGSLab. Next thing I think would be interesting is the touch and step safety plot. Now I'm going to remove my hash or my contours here by going to the display and removing that grid. And in my touch and step voltage group box, I will simply hit the View 2D. Here we can see the green areas, and this represents locations where our touch and step voltages are below permissible limits. The yellow areas represent locations where our touch voltages exceed our permissible limit, and red areas, if we had them, that would indicate both touch and step were exceeded. You can have these checkboxes enabled as well. This incorporates that surfacing layer that I added to my soil data. You can see when we include that, if they're surfacing throughout and an individual were touching a metallic component of the substation, they could be standing anywhere within this area calculation and be meeting their touch and step voltage compliance. You can change your reference for your safety plot by electrode. So I can change this from electrode 1 to electrode 1, or to electrode 2, and this changes my reference from my substation to my tank that's buried adjacent to the substation. We can also plot our touch voltages to the substation without that green, yellow, red mask. This way we'll actually see the absolute values of our touch and step voltages. We can do this for the step voltages. So last thing I want to do is just take a snap of this, save that from my report, save the touch voltages from my report, and I want to take an image of my safety plot. And you can access that report export in the summary tab. You can also view the images that you've saved in the gallery. Thanks all for listening. If you have any questions, please feel free to reach out and check out our website. Thanks. Bye.